G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. This is lecture 9 and part A. So everything I'm doing in part A will not be in the test in assessment 2. It will be obviously in assessment 3. So let's get into it. The work in the test will be in parts B and C. That's all revision. Okay, so this lecture I'm going to look at characterization in finite dimensional norm linear spaces, which is a big sentence, uniform convergence and equivalent metrics and norms. So all this is split up into subparts, uh, which all becomes hopefully a bit self-evident as we work through it. And I've got some questions at the end for you to do. Okay, so characterization in finite dimensional nonlinear spaces. We're just going to look at a bunch of points and how they apply. So compactness of the closed unit ball, a nonlinear space is finite dimensional if and only if its closed unit ball is compact. Now this reflects Rice's lemma, which says, in an infinite dimensional norm space, the closed unit ball is not compact. Okay, a nonlinear space is finite dimensional if and only if its closed unit ball is compact. In an infinite dimensional space, the closed unit ball is not compact. So for an example, and once I do an example, it seems pretty obvious. On an example norm on a linear space in Rn, the length of the vector is given by x1 squared plus x2 squared, blah, 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 plus xn squared, all square rooted, which is Pythagoras. It's effectively extension of Pythagoras. Example of a closed unit ball. Set up the set of all 2D points in R2, which is less than or equal to 1 unit from the origin. Probably could have written that a bit nicer. This is just a circle with radius 1. So even though it's not a ball in the sense of a three-dimensional ball, it can be classed as a ball even though it's actually a circle on in 2 dimensions. Compact, and what I've done here, when I've given these I'm giving these points, what I'm trying to do here in the blue is either give an example or explain a term. So if you know the term, yay for you. If you know example, yay for you again. But that's what I'm doing. I'm trying to explain each of the points about finite dimensional norm linear spaces. Okay, compact means it's bounded and it has, image is in the way there. Compact means it's bounded and it has a subsequence which converges. So that's what it means if you see the word compact. Okay, so hopefully those bits there help explain the black bit. Let's go to the next one. Okay, continuity of linear functionals. Every linear functional on the space is continuous if and only if the space is finite dimensional. So in this set here, I'll explain what these terms mean. So finite dimensional, for example, R2 or R3 or any R all the way up to Rn, they are finite dimensional. Even though that's got an n there, that n is not limited. That n is not unlimited. It's n. So you can say whatever number you want to put in as n. N is just given, as a generic term. So that's finite dimensional. Even though once you get beyond 3 dimensions, your brain really can't imagine what's going on. A linear functional. So this is an interesting term. You probably haven't heard it before. It's a linear transform, which you probably have heard before. So a linear transform, which takes a vector as input and produces a scalar. It satisfies 2 conditions. Fx plus y equals fx plus fy, and f lambda x with that attached to the x equals lambda fx with the lambda taken outside. So you can factorize that and take it out. Same here, you're splitting up fx plus y and fx plus y. Okay, and hopefully you've seen that sort of thing before, maybe in second year for a linear transform. In contrast, a linear function, now this you would have seen in high school, a linear function in Rn, probably just in R2 and R3, is where all values are in or 1 or 0, and I've actually thought of other ones where it's not 1 or 0, but you're looking at something which is a function. And these are just examples. 3x plus y is 1. That is a function in R2. Another linear in R3 is 5x minus 3y plus 2z equals 4. So they're just very simple functions. I probably actually should expand on this definition here, but really I've just put this purple section in to just try and delineate between what a linear functional is, which is what we're concentrating on, and a linear function, which I won't be asking you any questions on because that's too simple. Okay, third point. It's not too simple. Let's do that, sir, please. Continuity and closed image of linear maps. A normed linear space is finite dimensional if and only if the image of a continuous linear map is a closed subset of the codomain. So again, just going through explaining some of these terms. A continuous linear map, a function that is linear, preserves vector addition and scalar multiplication, and continuous, which occurs if and only if it is bounded. For example, matrix multiplication from R2 to R. So 2, 3 multiplied by 1, 4. 2 times 1 is 2. 3 times 4 is 12. 2 plus 12 is 14. So there we go. Codomain. So just in case you're not sure of that, the codomain is a set of all possible, let's see if I can go down just a bit, there we go. A set of all possible values that a function can have. For example, fx equals x squared. For x is an element of the reals. The domain is all real, but the codomain is all positive real. Okay, so the codomain is all real. You can put anything you want in x, but the codomain, which is y, is just going to be all positive reals, because reals, because once you square it, it will be a positive number. 4th point, finite dimensionality of the conjugate space. Now, hopefully you've seen the word conjugate. A norm-linear space is finite dimensional if and only if its conjugate, dual space, is finite dimensional. So conjugate space is equates to a complex conjugate. For example, V to W, where we say V and W are both elements of the complex space, with W being the complex conjugate of whatever V is. So if a function goes VW, and that's not the car, probably should have had a funny image of a car there, but if it goes from V to W, then we're going from, for example, 5 plus 2i to 5 minus 2i, so just the complex conjugate. Finite dimensional, again, there's a term there, finite dimensional, which was mentioned before, e.g. R2, R3, all the way up to Rn. 5th point, operator invertibility. The vector space is finite dimensional if and only if every right-sided invertible linear operator is also left-sided invertible, i.e. it's invertible. So what does that mean? For example, rotation in R2 is invertible, R cos theta, can be reversed as R minus cos theta. And that's not R minus, that's R multiplied by minus cos theta. For example, 2, a vector or matrix T in Rn is invertible. If we go T minus 1 equals the identity. So then we know that that's invertible, and pretty much you can figure out what T the minus 1 is, which we will do shortly, and you've actually got a question for that for homework. Pointwise convergence. Converges to a point. So this is pointwise convergence. We're jumping onto a new section here. For example, consider fx equals x to the n on the interval 0 to 1. As n approaches infinity, this function converges to f1, which is like 1 to infinity, which is still 1. And f0 converges 0 to infinity, which is 0, for 0 less than or equal to x less than or equal to 1. So this is pointwise convergence at both ends, but it's not uniform. And to show this, to make it more obvious to you, I've drawn a little graph. Thanks, Dr. Everett. That's great. So if n equals 1, we just get a straight line. If n equals 2, you've now got it being squared. So you've got a square happening here in between these where, for example, you've got a half. Well, a half to the 1 is a half. Let's say there's a half. Let's say there's a half. A half times a half is a quarter. So that actually curve should actually be a bit lower, but you get the idea that it does curve down. And if we do n equals 3, it will curve down a little more, and my graphs there are not very accurate, but you get the idea of what's happening. So it converges at both ends. You can see it's convert, but in the middle, it's not uniform. Okay, let's compare that to something which is uniform. We're going to consider fx equals x squared on n, again from 0 to 1. So as n approaches infinity, this function converges uniformly to fx equals 0. Okay, the whole function changes. So fx equals x squared to the n, if we're just looking at n equals 1. And again, my curve is probably not accurate, but you get the idea of what we're saying. We've got a squared for n equals 1. For n equals 2, it's still going to be curved, but it's going to go lower for n because you've got, divided by 2, where that is. N equals 3, now we're dividing by 3. It keeps going lower and lower and lower. So you can see that's happening. And taking the limit as x goes to infinity, let's do that algebraically. The limit as x goes to infinity of x squared over n gives you 0 over infinity at one end and 1 over infinity at the other. Oh, whoops, that should say n goes to infinity. Oh, whoops, that as n goes to infinity gives the limit n goes to infinity. This is traveling to infinity, not the x. My apologies there. Yeah, that should be n goes to infinity, n goes to infinity. This is x squared over n, and where n is infinity. So sorry about that. So here, what we've got, you've got the 0 over infinity at one end, which is there at this end, and then 1 over infinity at the other. And obviously, I could have written an arrow there saying, well, this equates to 0 over infinity. So both ends are going to go to 0. This is already at 0, and this one just gets lower and lower until it becomes 0. So that it uniformly goes to the 0 function everywhere, which is fx equals 0. Compactness examples. Explain why 0.5 is compact, but 0.1 is not compact. And it's pretty obvious here given the brackets, and this is just a very simple explanation. We're not proving it, we're just explaining it. So compact equals closed and bounded, which the square brackets represent that. So 0.5 includes the boundary point 0.5, which means it's closed and bounded. Hence, any subseries within and including 0.5 can utilize the endpoints as part of the series. 0.1 with curved brackets is not compact, as a subseries can be created which has a limit outside the bounds 0 to 1, but within the whole series, with the whole series within the bounds 0 to 1, excluding 0 and 1. In contrast, consider the series Sn equals a half, 1/3, a quarter. So in contrast to the blacks here, this is giving the two explanations, but in contrast to the black, let's consider this series. This is within the range 0 to 1. So if we start at 0, finish at 1, you're definitely within that range. Or sorry, start at 1 and go to 0. This is within the range of, you could say it backwards, 1 to 0, but we always say it in ascending order. It's in the range 0 to 1. But the limit, go there. But the limit of Sn as n approaches infinity of the series is 0, which is outside the bounds of the system, i.e. it's not closed. So if we just look at this converging, it's converging to 0. 0 is outside the bounds of the system, so it's not a closed system. Therefore, it's not compact. Okay, so hopefully that makes a little bit of sense. Possibly could have moved it. Yeah, doesn't matter. Okay, next point. So that's compactness. Last point is norm versus metric, and if you can try and keep this in mind, these two things do blur a lot. A norm gives the length of a vector as a real number. A metric gives the distance between 2 points as a real number. So they are really, really similar, but this is the main difference between them. The norm gives the length, so metric gives the distance between them. So that's how they're delineated. So an equivalent norm. A norm is a function from a real, or and this is a definition, from a real or complex vector space to a non-negative number. In other words, some positive number, which is commutative, obeys the triangle inequality, and is 0 only at the origin. Two norms P and Q are equivalent in some vector space X if and only if there exist a positive real numbers C and K, such that for every vector X, which is an element of X, C multiplied by Px is less than or equal to Px, which is less than or equal to K times Qx. So that is the definition of saying, okay, these two are equivalent if this is true. The most common norms are the Euclidean norm in real or complex space, and you will recognize these again. In Rn, the Euclidean norm is, again, the look there of Pythagoras, square root of each of the terms, summed and or squared and summed. And the Euclidean norm in Cn is just the same thing, but using z's there because you've got x plus iy. Okay. Equivalent metrics. So now we're going to try and give a difference. There's a pretty decent article in Math Wolfram called Equivalent Metrics, which you can have a look at. Two metrics G1 and G2 defined on a space X are equivalent if they induce the same metric topology on X. This occurs if and only if for every point X0 in X, every ball with a center X0 with respect to G1 contains a ball with a center X0 with respect to G2. So what that means is here, I've written out a verbal explanation of this. You've got this ball is this and this ball is this. And here I've written out the explanation. The ball, so B, center X0, there's X0, radius R1, is defined as X being an element of X, is X, where the distance from XO to X, so there's a distance from XO to X, is less than the radius R1. So that's the trying to say it out loud, so it hopefully makes more sense to you. So what is it saying here for equivalent metrics? This ball contains this ball. And if you think of two balls which are equivalent, well, it's going to be the same ball, isn't it? Funny that. Last thing is the Manhattan distance, which is often called the Manhattan norm, I've noticed, but it's actually, it would be classed as the Manhattan metric, not actually a norm because it's not a vector. The Manhattan metric is based on the concept of a taxi, and you can Google it. You can Google the Manhattan distance or the Manhattan norm, whatever you want to call it. But from my analysis of it, it should be the Manhattan metric or distance. It's based on the concept of a taxi traveling in New York, and I've drawn a little map there of New York. Don't you love it? It's just a bunch of green squares. I haven't written any towns on it or any street names. The Manhattan is based on the concept of a taxi traveling in New York. Since the layout of New York is a grid, the absolute distance of the taxi travels can be measured by the absolute differences of each city block. And effectively, this again is using Pythagoras, or that sort of thing. So, for example, find the distance between 2 points A, x1, y1, and B, x2, y2, which are obviously in Manhattan. You're going to calculate x2 minus, that should be x1 minus x2. We're missing some corrections there. That should be x1 minus x2 plus y1 minus y2. So A is 1, 1, B is 5, 4. So 1, and again, that should be x1. x1 take x2, y1 take y2. So we get 1 take 5, absolute value is 4. 1 take 4, absolute value is 3. 4 plus 3 is 7. So therefore, the taxi must travel 7 blocks in some combination, such as 4 vertical and 3 horizontal, to reach its destination. So fairly simple, again, utilizing the Pythagorean triangles. And really, that's a lot to do with distances and metrics. Can be a lot of things that we've spoken of this lecture can be applied to vectors and matrices, which I've got in some of the questions. So here are some of the questions, or here are all of the questions. Determine the distance between the following vectors. These are pretty straightforward, just using that Pythagorean type of square root. The same you'll apply here for the matrices, using it with each term. Then some true-false questions to make sure that you actually understood the notes, and explain the condition for invertibility of a matrix in Rn, and then produce the matrix which shows it's invertible for that one, and then prove whether the following is a linear transform for xy. Okay, that's it. God bless you. Hope you have fun doing some of these questions, or at least enjoy it and makes your brain think. God bless you. Stay safe, and I'll see you next time. Bye.